so I don't jump the gun. Recording started. Okay. Great. Go ahead, Mariah. Was that your thumbs up? I think that was her thumbs up. Okay. Okay. All right. Welcome to the Go user group. Our not March. I forgot to update the date. I'm sorry. This is April 7th. Just quick reminder for those who haven't been here. I think most of us have, but microphones are good. Your conversations made up and uploaded to YouTube. If you want to get famous, that's a good way to do it because we're going to get thousands and thousands of views on our MLOps meetups, or our Go meetups. Not even the right meetup, gosh. We do have a papercall.io link if you want to submit a request to speak that way. Honestly though, just come talk to me, come talk to Carson. Hit us up on the Forge Slack, which I'll talk about here in a little bit. We would be happy to help get you set up. If you want to do a full talk, that's great. If you want to do a lightning talk, that's also great. Just let us know. We'll work around whatever your preference is. And we are doing standard lib packages. That's sort of like the default topic. So if you have a standard lib package that you're really excited about, go research it a little bit, throw together a talk. That's sort of the focus for the meetup for the next foreseeable future. Hiring, I know a lot of people come to these to network and to look for people to hire or to hire folks. Forge Utah is the best place to get involved with that. We have a jobs channel, sort of woken up a little bit lately. I've seen more posting happening there. There's also a place where you can drop your resume and network with folks there, explicitly looking for jobs. But also there's lots of fun stuff that happens there too. So if you come for the jobs, stay for the fun conversations about all the other stuff. Weave is hiring. We want to make sure to give a shout out to Weave because they're hosting. They paid for the food tonight, so they've been good to us. Getweave.com/careers. We have some available engineering positions open. Go check them out. I know there's positions available for the MLOps team, which is the team that I'm part of. I think there's a couple other positions available as well, mostly for back end. But yeah, if you're interested in writing Go professionally, getweave.com/careers. Yeah?
So a couple things. You also know if Weave is hiring people within data or cybersecurity?
I don't off the top of my head, I don't think so, but the careers page is the best place to check that.
Okay.
Yeah, and if you go on the page and find a job you're interested in, talk to me or Carson.
Okay. And then could I get the password to the Wi-Fi, please?
Yeah, so Weave guests, and then it's care space more, all lowercase.
Wait, what's it?
Care space more.
Care space more.
Yep.
All one word?
All lowercase.
All lowercase. Perfect. Okay, so I'm going to go ahead and turn the time over to our speaker. It's the math package today, so I love the title of the talk. Go figure is a fantastic title for a math package talk. But yeah, go ahead and turn the time over and get the talk started. So,
Clark?
yeah,
Mr. Math is awesome. Right.
You join the meet.
Yeah, you joined.
So, and I can ping you the link if you need it.
That'll be fast. Should have sync that up as well. That's something we normally do as part of our.
I want to give Mariah one this.
We won't.
We're keeping this in for posterity.
No,
It's very
We don't
important.
need to, if it's too polished, no one will believe that any of the content's real. No one's gonna look at this and go, this is AI generated. Human. Yeah, to err is human, so I'm really human. I can attest to how human I really am.
Here is the meet link. this can be in point five.
Barrett says hi.
Anybody got any good jokes in the meantime?
It didn't,
No idea
it
what
didn't work.
You write a text space, or did you put in an actual white space?
So we.
I think. Oh, like, when you say space, you're talking like hitting the space bar. Okay, that makes a lot more sense, thank you.
Okay, we're actually gonna start now. Hello. My name is Doug. Background. All the information I'm gonna say is here, which is it's for your entertainment. I'm a senior software engineer at a company called Cedar. It's based in New York. Used to work at Neighbor across the freeway, which is where I got to start working with Go, which was fun. And I do have April as the date, so that'll be the recording. This is going to be a tour of the math package. This sounds like I'm going to sell you something from the classroom to production. But we're not actually going to talk about much stuff you would do in a classroom or much stuff you would do in production. We're just going to talk about math, and it's fun. So hopefully you maybe like math a bit. If not, I will try my best to make this entertaining. But I'm going to start off with a train, one place, another train, another place. When do they meet in the middle? And what you don't realize when you're a kid is you actually just started doing your algebra. You're on your way to writing our deep neural nets that are just doing algebra. But you know, they don't teach it that way. Anyway, we will be covering math and its friends except for random, which gets its own chunk of time. One wants to do it, you're welcome to, but I will probably try to do it in a few months. So we've got math complex, math big, math bits. Complex is a fun one, which is actually what we need to think about presenting on this topic, because I was reading the Go spec and learned that there is a primitive type called complex 64 and complex 128. So speaking of primitive types, we're going to talk about how to represent numbers. We're going to go over this. This is not specific to Go. It's going to feel kind of mathy. It's going to be fun if you enjoyed any courses or YouTube videos on how to store an integer. I'm just going to go over it because a lot of the math package is useful because of some of the trickiness that comes out of trying to represent numbers with a limited set of bits. So we'll start with integers. We've got this is not that scary. This is just like set notation. I'm showing you the integers get a z, the natural numbers get an n. You know, the natural numbers, there's no such thing as a natural number primitive, but the Go standard library for math, let's see, math big actually has a nat type instead of, it's like wrapping around a uint. Anyway, so we've got, you know, integers, we've got negative, positive, they're whole numbers. We've got our natural numbers, which we will start at 0. Some people will call that blasphemy and say you should start at 1, but as people that aren't writing in other languages that decided to index based on 1, you'll all be with me on 0, hopefully. And these are all, what we're looking at here is base 10 representations. That's our favorite that we know and love. So let's start with non-negative integers. Okay, so binary, not that scary. It looks scary. It's hard for us to read maybe, but it's just a base 2 number system. So base 10, you got your ones, tens, hundreds, thousands, etc. In powers of 10. 10 to the 0 is 1. 10 to the 1 is 10. We do the same with binary. We have 1s, 2s, 4, 8, 16, 32, 64, and we're just doing everything in powers of 2. And that like classic binary representation is how we're going to show our like unsigned int. Is each of these is 1 bit, and it's either 0 or 1. I've got this fun little notation with the subscript 10 and 2, just so when we're showing decimal and binary in the same spot, you know which one it is. That's the base system. That's all that means. So we got like 0, 1, 2, 3, etc. You're here for Go, so I'm not going to spend too long on this. If we want to show negative numbers, then we get clever. We have bits. That's all we have to work with. So you can be as clever as you want. We're going to take the first bit. This is all 4-bit ints, which you don't ever have to work with probably. We're going to take that. There's a plus or minus. I made that notation up. Everything was made up. That's really signs of the sign. We got between a 0 plus 4 plus 2 plus 1. We have our 1, 2, and 4 all 1s and 0, yeah. And then I said the first bit is going to tell us if it's negative, but it's not quite that simple. You really want to figure it out. The way we do it is something called 2's complement, where you invert. We're going to flip every 1 to 0, every 0 to a 1. We're going to add 1, and then that gives us our number. In this case is 1, negative 1. So 1, 1, 1, 1 in our 4-bit signed int world is negative 1. Yeah. And so with 4 bits, we could previously store more values. We've given up our range a little bit by taking up a bit for for being able to represent negative numbers, and we'll keep seeing that pattern throughout this. Yeah.
So, I don't know, maybe you're gonna cover this later in the talk. Are you gonna talk about why we choose to use 2's complement instead of just using that sign?
No.
Okay,
No.
okay.
We're not going to cover. We're not going to go into that. I'm happy to talk. We're already done with the ants. We're moving on to floating point, which might get scary. So with what we're doing before, it kind of felt a little more analogous to our base 10 system. Well, then we have fractions. How are you going to represent something between 0 and 1? We get clever again, right? We have a number of bits we can use. So as long as we all agree how we're going to do it, we can do something systematically to represent numbers that are fractional. And I'll talk about that a little more. Yeah?
What exactly is the mantissa, and does that have anything to do when it comes to fractions?
Yes. So breaking it down, so here, this is showing you for floating point, we're going to use IEEE, what's that, electrical systems engineers, I don't know what the other E is, internet group. This is a standard, IEEE 754, and it's basically just a spec of how we're going to do this. So we're going to use our first bit for our sign bit, positive or negative again, and we're going to use the next 8 in this case, different size of floats, but so we're going to use 8 for our exponent, and then we have our mantissa. Now, everything's color-coded here. What we're basically building is scientific notation. We use something like 3.4 times 10 to the 8th, but instead it's like base 2 scientific notation. So we're going to build out positive because our sign bit is 0, and our exponent and our mantissa is this fractional part. It's always 1 point something. In this case, you can see we've got our 4 1s right here, over here, but we have lots of precision. We could keep going. And then our exponent, when you do all that math, you get this number is 79 in base 10. So yes, that mantissa is our, like, everything following the 1 in our scientific notation, be able to show fraction numbers. And
represented integer.
in this case, person I stole the slide from because I didn't want to build this whole thing out myself. Chose an integer, which I think their previous slide, I should have sourced from, but this is not mine. I fault whoever made it. But yes, it was an integer, which is kind of boring. Yeah.
So the 1.001111, that's not a base 10 number, that's a Boolean number, right? Or that's still a base 2.
Yeah, that's still base 2.
And so the stuff after the decimal point, if I'm remembering correctly, is that like 1 over 2 to the power of that position?
Yes, or you could think of it as like 2 to the negative, now that we're on that
Yeah,
side.
okay. Right.
Yeah.
Yeah.
We're going like halves, so like in decimal, right, we go like tenths, 100ths, 1,000ths, go in the other direction. It's the same thing, we're going in reverse, but we're doing half for the negative powers of 2, negative powers of 2, so they end up being like 1/2. 1/2 to the power of whatever we call it. Now, we only have so many bits, so we only have a certain amount of precision, meaning there are some numbers we can't represent. And so we don't know how to make these decisions, but we have to like round, flip, or truncate, and we get fun errors because we can't represent everything precisely. So here's a very contrived example where I definitely could have used a loop, but I didn't. I use a loop later when I revisit this example. And you're like, oh, we're going to talk about this example again. That sounds super exciting. Well, here we have 1/11th, and then if we add 11 of them together, we should get 1. I want to guess.
A lot of zeros in between.
0, 0, 0.
I've had issues with Playground, try just reloading.
There we go.
There, yep.
You're right. So now we've got this extra 2, which might be negligible, but you have to know that you might have it when you're rounding, and you might be adding numbers more than 11 times. So you get all these rounding errors, and you get issues there. So when you're like representing financial data, you want to probably use like integers and track sense, that kind of stuff. But, oh, thank you. So the more operations you do, the more kind of rounding errors you can get. We can only get so big, we can only get so small, so we can get things we call overflow when we get really big, underflow, which isn't like really large negative numbers, but we're getting so super close to 0. So lots of numerical methods for solving mathematical problems, and doing like division over and over again. Sometimes that gets really small, and then you're dividing by something really small, and then you get a really big number. You get all sorts of things you have to account for. And if you look at some of the functions we're going to look at later in the math packages in the standard library, they're doing little tricks along the way sometimes to prevent overflow or underflow or account for rounding errors.
Yeah, fun fact, this is one of the things that makes it hard to train deep neural networks. Because when you have lots of layers, your floating point numbers can get very, very close to 0, and then you lose the signal, and then you can't backprop, and then you can't train. So this is one of like the painful points in the AI lab when you're like, oh, my stuff's not learning. It's like, oh, floating point error just hates you.
So integer types in Go. Go does have an int and a uint, unsigned int, non-negative. Alias, where you can just say int, independent of how many bits you're using. You can also specify through 64. If you just do this, it's dependent on the architecture that you're running on.
The largest one that it can, I think,
Yeah.
based on the architecture. So for most of that's 64.
Yeah.
But not always.
If you're doing stuff on like embedded systems,
Oh, you're right, it'd be lower.
Float doesn't have that. We've talked about like there's all sorts of stuff that could go wrong with floats anyway in precision, so you might as well be explicit, and you don't have the same, like it's nice to be able to just say int when you're doing your like for loop and you have your iterator, like, and it's closer to the way the machine instructions are working. And the compiler likes it, but there's no reason to do that with floats, so you have to specify, and most of the math package is gonna be expecting float 64, so if you are not dealing with float 32, you have to cast everywhere, which is kind of annoying. And then complex numbers. So if you've seen this before, 4 plus 3i, I here being the square root of -1, this is an example of a complex number where there's this real part, this imaginary part, you have like 7 minus I, and so we actually end up with 64 and 128 because, again, just like floating point, we were being clever and we said, okay, we can store the exponent in these bits, mantis in these bits, a sign here, and we can use that to determine our number. We're just being clever again. These are actually just floats under the hood. So we have, for complex 64, we have a 32-bit float for the real part, like 4, and the imaginary part, 3. And we just keep track of the fact that there are these two numbers. We basically get like a tuple of numbers that we can use when we do our math. And then complex 128, it's because we get 64 bits for each part. We're using 128 bits. You can write that notation plus 7i in Go. It compiles and it knows it's a complex number. I don't know if it's accidentally done that as a it meant to do like 4 times I, and I was your iterating number. But yeah, if you read the Go spec, you can do that. So we've got our like Z1 is 3 plus 4i, 2 plus 7i. You can do arithmetic, you can add them together, multiply them, get those results. And then there are also these keywords in Go, first classes, and even though almost no one's using them, do real, match, it'll reduce that down to just the real component or the imaginary component, which is kind of crazy to me. I think it's cool. I studied math, I love math, so it's kind of fun, but I don't see myself really needing to pull off the coefficient of the imaginary component of a complex number in my day-to-day with Go.
Yeah, so, I have 2 things. One question is, why did they put that in there, if you have any idea why? And 2 is, I've seen people use this in advent of code for vectors. When you have like x, y coordinates that are always linked together, rather than make a struct of x, y, they've just kind of cheesed it with, I don't know, the only benefit is you get free operations for like the arithmetic, right?
Yeah.
So they're too lazy to write like vector x dot add vector y, so they do these, and then they can just add and multiply and like the vectors together. And but that's the only use case I've ever seen, and that's just for like, you know, fun code for challenges. Like, do you know why they have it?
So if we look at the people who created Go, they also enjoy math like I do. And I could see them, one, being convinced, you know, like very opinionated, right? So it's like convinced, yes, we need this. It's been, you know, like C does have a way to add complex, and they kind of modeled some of that the same, but it's like built in. But I could see just getting carried away or being opinionated that we need it for rigor. But also it is useful in signal processing and electrical engineering problems. It can be useful in cryptography, but not usually. There's lots of stuff that supports cryptography.
Don't do that.
So it's not, the only place that it's referenced in the standard library outside of itself and the complex package that helps do the operations is, I think, marshalling and unmarshalling, specifying like how it should be.
Oh, okay.
Marshalling or unmarshalling. But I didn't see anywhere in the standard library where it's used not for itself, basically.
Okay. So it exists to exist.
But I love that idea of just like coordinates. If you have two numbers you need to track and add
If you have two floats, you wanna,
floats, yeah.
They picked the wrong advanced math thing. They picked this instead of matrices. Have native support.
Fair enough, yeah. So does that mean if you try and square root a negative number, it's just gonna throw? It's not gonna return you one of these?
If you do math.square root, it won't compile because it requires a float 64 type. If you do math complex, which has its own square root, it'll work.
Okay. You gotta read your manual.
Okay, we haven't even gotten to the math package yet. I should probably speed up a little bit here. We're going through just like, we can do math without the math package. Should be no surprise to you, we have these operators built in to go. Add, subtract, multiply. We have bitwise operators too. They're also mathematical operations, especially when we're dealing with binary. We have and, or, XOR. Go has a fun thing, bit clear. We have our ampersand and, what do we call it, caret? Not a caret. I want to say like a circumflex accent. That's linguistic. And then bit shifting, so taking all your bits and moving them like one spot over or one spot back. In a way that loses it, you're not rotating. But if you wanted to, you'll see you can later. The bit clear is, that's actually really interesting. It's not and, which allows you to like create a mask. You want it to like, just like we can store floats or complex numbers just by using our bits, you can store any information you want in your bits. So you could say, this config has 16 options. Here's my uint 16 that represents the user's configuration. And it's very compact and storage efficient. You probably don't have to do that. There's historically been a lot of that in software engineering when space used to be really tight. But now we just kind of believe that we're going to have awesome hardware. But
it's also a lot more efficient if you wanna store like, I've got 1,000 configuration options, flags or whatever. I don't wanna ship 1,000 values in a JSON blob. Here's a few ints.
yeah, especially, and if you're sending data between systems or over a network, it's mobile. Yeah.
My one use case for bits as flags has been in the core library we have internally where we attach attributes to the context that kind of follows the function executed. And those attributes need to have like, this is intended to be used with logs or errors, or like, it's one of those things where like, we're creating lots of them. There are lots of these attributes constantly throughout the code base, and I didn't want every attribute to have 20 bools. That's a lot of memory for something that is used constantly and made constantly, where the one use case, like, it's all kind of hidden behind a lot of like stuff, because doing those operations isn't super clean. So I kind of hid that in the usage, but behind the scenes it was actually all 20 of these options are one integer behind the scenes, and so it's really, really efficient for us to track like aspects of whether, you know, whether this user ID should be logged out or returned with errors or any of that stuff.
Yeah, sure.
Use cases even still, even with great hardware, because a lot of bools can take up a lot of space very quickly, right?
You're just encoding information in a specified way,
Yeah.
structured. If you wanted to do like, people have ever looked at genetic algorithms too, as a way to solve problems. It's very efficient to have your new evolutions. They're basically like strings of bits that just do a bitwise operation of the next generation. They're really cool. We should do a genetic algorithm.
Adventive code is a great place to use some of these tricks, right?
Okay, now we're to the math package. We made it. We made it here with me. I think everyone's awake. But I did say we're going back to math class, so if you were prone to it. Let's look at constants. I'm very proud of my LaTeX rendering here. We've got pi, e, and this is pi, but this is actually a little variation. And there's some big debate in the people doing math about which one you do. But we have these constants all available to us. The last one, that's the golden ratio. And these are all stored as floats that are constants in the math package that are available to you, as well as some kind of meta information about what's our max score, max and yeah.
I'm fairly certain that you can use like the Greek letters, right, as variable names, because Go supports Unicode. So in theory, you could actually use pi to store pi.
No.
I think you can.
That was variable names, but the constants aren't named that.
The constants aren't, but I think it was maybe a missed opportunity.
Yeah, maybe.
Well, it's not a,
I'm trying to remember if they do. I know some languages do support Unicode.
The trick is, if you were to take math.Py and at start of your code, say, you know, I don't think variable names in Go actually let you have full Unicode range. I think we have a restricted.
They should, but do they?
But that aside, if you were at the start of your code to go pi : equals math.Py, you would get different results potentially than just using math.Py directly. Because Go constant floats behave differently than variable floats. Just a fair warning, like, if they're constants, anyway, there's no reason to rename, you just use the constants in there, I didn't know they exist, sorry, we're
more problems with floats, and the magic of floats.
in the magic floats. How many digits of pi are in there?
The precision, let's see, I think I'm just straight up doing.
Okay, so that's the whole thing, so, I don't know, that's what, 20?
15.
Which, if you want to successfully get to the moon, you need like 3.14, maybe 3.142.
More than enough.
We have people memorizing all these digits of pi, and in reality,
That's being important pretty
it
quickly.
really stops being important pretty
You also need to not forget to convert between inches and centimeters.
Yes. I actually had a issue here as, well, there's an example later, when I did something in kilometers and then in miles. Lower stakes than space. And NASA, if you go read the NASA coding restrictions, it's kind of like it's impossible to pass their linter, have a possible infinite loop. Every loop must have like max iteration on it, and other things like that to prevent things you care about when you're sending people off into space and around the moon, which is awesome.
And yet they allow Outlook.
Don't even get me started, yeah, that shot.
Special values, so we got infinity, not a number. In other languages, if you divide by 0, you get a problem, just so you know, in Go, you don't. Anyone know what I get here? It's not gonna
Pan?
Not gonna pan.
Not a panic.
Infinity.
Huh.
It's infinity.
Hooray.
As you approach. As you approach 0 from the right, so we're getting a really tiny small number. That's the number. Yeah.
Oh, God knew so much about. Just speaking from on high.
Another thing I forgot to include here is, I'm pretty sure, so NaN doesn't pass an equality check with itself. So,
And is it like infinity or?
like, if you do NaN equal NaN, it'll be false.
Just like
Predicate resolves to false.
In Go? I don't even know how you do NaN in Go.
Math dot.
Oh, I see, sorry, there's a math, okay, we just don't have much NaN, gotcha.
Anyway, not that you're likely.
What you don't, is it is
lines, you gotta read between the lines.
Sorry, sorry.
Oh, you're good. So now we're
You're in the right place, Mariah.
gonna. So let's talk about some functions that you might remember depending on your TI 83 plus here. My graphing calculator I used was older than this. But it had all these functions. So you see all our buttons. Most of those buttons that aren't internal to the Texas Instrument system are functions that you get in our math package. There are like 8 of these slides. They're not super interesting. I'm going to try and highlight some. I'm not going to do all of them. But you are probably familiar with absolute, value, max, and min. You've probably used those. You might not be using max and min as much. In your new versions of Go, you don't have to do math.Max to compare values that are comparable or comparable.
How British am I feeling today?
We've got other things we can do here. This one I want to talk about, use multiply add is what FMA is. It's, you're passing it the values, 2 values that are being multiplied and a value that's being added. And you're like, why would I need that? I talked about, we can get things like overflow, underflow. So if you're doing a lot of multiply, add operations, this is optimized to prevent as much error as possible. And when you're doing your, when you're writing your matrix multiplication from scratch to train your LLM and Go, that's what you're doing when you're multiplying matrices. When you're doing linear algebra, you're just like multiplying values and adding them over and over again. And so this is optimized to try and
So
you probably aren't running into issues with your multiplication and addition. But if you're doing a bunch of them over and over again, you want to be using this.
Are these all generic functions now?
These are all float 64 parameters coming in. I guess I got the whole signature, which I don't really. But they're all well documented on the math page.
What's copy sign do?
Copy sign. Do I have that one in my notes? I don't have it. If someone wants to look it up and share it with the class, that'd be great.
That's fine.
I think it gives you the same value back with the opposite sign.
I assume sign bits returns you what the sign was, but, all right, I'll believe it.
Copy sign returns a value with the magnitude of f and the sign of sign. So you pass in f and sign, which are 2 floating point numbers.
That was mostly right.
Oh, interesting.
Yeah, in the back. We have more functions for rounding and decomposition. You've probably also used those top ones at some point, because we do want to end up doing rounding. We can do round, you can round to even. So if you wanted to specifically only get even number, round to even. Truncating, and then mod f, which is more detailed than you get out of just a remainder. It gives you both components. How many times does a number go into the other number? And what is the remainder that doesn't go in? Which is useful when you're doing abstract algebra, which is useful when you're doing cryptography, which, again, disclaimer, don't do your own cryptography.
No, totally do it.
Why would I,
That disclaimer was for you, Tom.
why would I use that and not just the mod operator?
If you needed to know, it's basically like doing division and mod in one. So if you needed to know, like, how many times does 7 go into 18, you needed to
And you
know,
need to
for
know
some reason you needed to
7
know
over
it
18.
twice, and you needed to know where the remainder was 4. Which, again, the only use cases I have come across are to do more mathy things to do cryptography.
Used in advent of code as well, because otherwise you have to do the same operation twice.
Yeah,
Throws
it's
away
more
half
efficient
the
than
time.
saying what's like x divided by 4 and
X mod.
x mod 4. A lot of the math stuff is written in
Assembly?
there's a specific name for the way it gets used in the Go standard library though. But yes, it's closer to it's optimized to get machine instructions that are gonna be faster than some of the stuff you might hopefully do, but it doesn't matter in most cases until you're doing something over and over. Third question.
When I look at the math package and having to like, if I'm in integers and I have to like cast 2 and from a float 64, right, I know that there's rounding errors, and so like, I just avoid it. I'm like, I'm sure it would be fine, but why would I use this math.ceiling just in case something weird happens? I don't know if anyone else feels that way, but it just makes me feel icky going to a float and back from a float.
Yeah, especially when you're trying to do like something just like absolute value.
Yeah.
Like, I want one that's just ints. And I actually have written for Advent of Code, I wrote a little integer absolute value that doesn't do the float casting.
Like, is there not a like time when the integer would exceed what the float can represent?
Yeah, if
Can
you
you
have
answer-
numbers, you would probably end up with floating point error as well.
Sorry, was the underlying question, can an integer be bigger than what a float can represent?
Yeah, like at int 64, if you're max int 64 going to float 64, you're preserving it.
No, you can go up to, what, like 19 quintillion 64-bit ints. And with floats, you can go up to like 10 to the 70. Is that way too high? That might be but as a matter of precision, we also have math big that we'll get to in a second that does allow you for, if you have really big ints and you know they're ints, get even bigger. I don't know. I don't know the answer. A lot of people complain online on Stack Overflow, if you remember Stack Overflow. I was on there earlier today. It's like, oh, hello, my old friend. I was like, why do all these math operations only have float? Wouldn't it be useful to have ints? And then there's always the classic Go response of, it's not that hard, go do it yourself.
Yeah, I'm surprised a bunch of them haven't been just made generic functions. There must be some backwards compatibility reason that they're trying to maintain to not, otherwise, cause, right, cause like, not all of them, but there's probably a bunch of them like, absolute, like.
Yeah, it could include multiple ints and whatever. Some of it might be because it's optimized.
It's true, it's not,
might not be.
it's not just pure Go, it's going into these other languages where it's like actually harder than you think for that package to, yeah.
Usually when you're dealing with floats, the thing you want to think about is not the language, but the hardware it's running on, because that's the whole point for their existence. Otherwise, we would not give a single shit about floats. Like your graphics card, they only work on floats, for the most part.
And yeah, it's annoying because floating, yeah, it'll be different depending on the hardware.
Yeah. So if you want to like do like precision stuff or like money or something, you don't do any of this. Like the math doesn't math for any reason other than the hardware that's doing the thing that you want to do with the math.
You want to skim pennies off the top.
Office space isn't.
Disclaimer, don't embed floats. So a couple call outs, we have uroot, if you ever wanted that. And hypotenuse. So if you find yourself taking the square root of two numbers that you're squaring frequently, this will do it much more efficiently and avoid issues.
You know, just this morning.
So if you were writing a graphics library or a game engine, you'd be doing this all the time, and so then it's actually useful. But you're probably not doing that. But maybe you are for fun. Lots of log options. Logarithms. We got trig, sine, cosine, tangent, as well as their inverses. That's what the A is: arc, sine, arc, cosine, arc. Hyperbolic sine, all that. Okay, more math. This is just because these are cool. It has the error function, which is the probability distribution function for a normal distribution. So it's like an S curve where you're, if you think of a normal distribution, it's your bell. basically accumulating. So instead of it starting to go down, it just keeps going up, like summing all of that together. You get an S curve. This is the definition of it. But you can do it. You can do multiple things. You can do inverses. If you needed to create some kind of score that you wanted to fit kind of a normal distribution, you could use that. Gamma, if you've never heard of the gamma function, this is Euler's gamma function, which is the continuous representation that's closest to a factorial. If you pass in an integer into this thing, you actually get out, like, if you pass in 3, you get 3 factorial, so 3 times 2 times 1. But then you can pass in 3.2 and get a value out that makes sense, even though there is no definition of 3.2 factorial. When are you gonna use this in your Go code for your, like, I don't know, like, does Kubernetes use this? No. And then Bessel functions, these are for like wave dynamics. You have of the first kind and the second kind. I didn't include that. But, yeah, it exists.
Fancy.
More excuses to throw some math up there. There's some useful things if you were to do conversions between bits, and like if you want to see representation in bits of floats. Bit log, first bit log. You can go look at those. Not worth them right here. We talked about some of this. You can check if a number is infinity or a number. Next to after is interesting. This, you pass in a float and it tells you what the next float that you can represent exactly is. Because there's some that we just, because of our limitations of how many bits we have, we can't represent every number in the continuous realm of numbers from negative infinity to positive infinity. So you can, if you needed to know for some reason, you could say, what's the next one I could do? And it tells you that.
Is the default 64, and that's why there's 32?
I believe so.
Weird.
And yes, it is a lowercase a. I thought it was a typo. I had to go.
Does it fit the style guide?
Let's do an example. So if you wanted to, you could compute values of this function for fun. So these are all things we just saw. And so you just write them out, I've split them into terms here. We've got our exponent, our power. You know, you can chain it all together. You can write this function as a function. I even called it f. It takes in x, and it returns out a value. And it works, which is cool. You want to know what it looks like? That's what it looks like. And it only exists for positive, non-negative numbers. It oscillates wildly, growing logarithmically after that. Super fun. Okay, let's go to something maybe more interesting that you've probably seen or thought about. I don't know. Haversine distance. When I go from here to here on the Earth, I am actually on an arc. The Earth is not flat, contrary to unpopular belief. So we have this cool way that you can take latitude and longitude, you convert them to radians, and then you take their delta, you use the Earth's radius, you compute the arc distance, and that gives you, you're in Google Maps or something, it says this is the distance between point A and point B. That's the actual kind of stuff it has to do, although in Google Maps it's accounting for streets and stuff, not direct.
Yeah. Matters probably large distances, right? Like, it's almost not different for really small stuff.
Yeah, so we could look at like, this building to MIT, Cambridge, Massachusetts. We're gonna throw in those coordinates. And everyone on the call knows exactly where we are. To the second, and then I thought this would be fun. Alert Canada is very far north. It's the northernmost continuously inhabited place on the Earth, and they have a Tim Hortons there. It's a military base, and
That explains the name.
yeah, yes, that's why it's called Alert, because it is a monitoring station for the Arctic. For some reason, in like the 70s and the 80s, they felt like they should build that. So we're going to compute the distance to the North Pole, which here's a fun thing. These are both the North Pole because the North Pole doesn't have latitude and longitude because it's a point. So these should be the same if we built this right. Are they going to be the same? Are they going to be the same? Oh man, they are. Yeah, so and if you're in Alert, you're only 830 kilometers from the North Pole. Which this is the one that was in miles and kilometers, and I probably should have gone with miles. but that's maybe not super intuitive. But that's pretty close to the North Pole, as close as you can get if you're going to live there all year. And then, yeah, if you wanted to go to MIT from this building, you're 300 kilometers. This would have been more interesting if I'd shown you the naive non-arc.
Yeah, I wonder what the difference is on those.
So it's longer, right, because we're not going through the Earth. I don't know the exact difference. We're gonna keep going.
You don't get that.
There's a complex package, like I mentioned earlier, and so it's got a lot of the things we just saw, but for complex numbers instead of float 64.
What do they have against vowels? What do they have against vowels? What's wrong with vowels?
Have you ever programmed?
Yeah, sure, that doesn't feel that much shorter.
No, it doesn't feel, but yeah, in this case, it's like,
And bits and big, they did the whole thing.
the whole thing, yeah, it's not BTS or BG or whatever, like, I don't know, it feels like they chose that one to arbitrarily make unnecessarily short.
Nope.
That's just a name.
So we've got our same kind of functions. If you needed to, do the hyperbolic arc sign of a complex number, you can do that. Fine. I mentioned square root, that was asked, it's the square root of a complex number. You can do that and it'll work. And then we have additional special values here. So these are functions. Here, you can pass a number to infinity, get the kind of infinity you want. So all it's really going to do is actually take the sign of that number, get positive or negative infinity. So these are maybe more interesting. These are things that are actually done commonly with complex numbers. So your absolute value, you're actually taking the magnitude. Quickly, complex numbers can be thought of as a plane where you have the real part and the imaginary part as your x and y, which is exactly why people use it for x and y. And so that magnitude is going to give you like the Euclidean distance, like between from the origin to your point. You can also think of that then in polar coordinates as the angle. I'm sure the people on the call can see my little hand here, but the angle, theta, and the magnitude r. And so you can convert back and forth, which is cool. And then the conjugate, complex conjugates are useful in math. I have not found a use for them yet while writing my code.
Is conjugates the only thing you haven't found a use for?
I'm using all those other ones. I'm constantly going between polar and rectangular coordinates for representation of complex numbers.
Yeah, that makes sense, okay.
As we all do.
Mandelbrot set.
Yeah.
We got our friend, the French mathematician. This is learn about fractals. You've seen this picture. The YouTube video thumbnail about fractals, I'm sure, has like some person brightly lit doing this, and then there's like a Mandelbrot set in the background. It's like
Mandelbrot and Julia.
the way we basically define is we'll start with the number z, and then we'll like update it with point c, square it. Anyway, we're gonna make sure, like, if z, the magnitude of z, the absolute value, is less than some value, so it's bounded, then z is in the set. But if it's too big, it's not in the set. I don't want to go through all of it. But here's the code, and we got this fun little palette so that we can apply it. And you might actually know what I'm talking about if you don't get thrown off by the ASCII. It looks kind of like this, really small, infinitely.
Just let your eyes go blurry, it's a lot better.
So if you wanted to, in your Golang powered terminal user interface, show a user this fractal set, you could do it without too much issue. Oh, here's another, you can construct a complex number from the real and imaginary parts as well. An example of that, but instead of doing like 4 plus 3i, if those are variables, it's much easier to just do it as complex. Bits. So remember our friend, the unsigned int, so we have like 13 in decimal, it's like this in binary, got a few ones in there. So bits package gives us some useful functions to do things like, how many ones are there? I don't know, I don't want to count, I'd rather run this code. there are 3 ones. Wow, that was right. How many leading zeros are there? How many trailing zeros are there? And those things are useful, especially if you do want to like pass your config as a bunch of bits around and you have it in a specific order or number of configurations is important. You can count bits. So lots of functions. I'm not enumerating all of them here. I did mention rotate. So if you did want to not just shift your bits, but like have the leftmost bit or the rightmost bit wrap around, there are ways to rotate left or rotate right and rotate everything. Again, I'm not using that.
So rotating is a shift plus moving it around, or is it?
Yeah. So it wraps. And if you rotate n bits, you rotate n times, you get the same number back out. And length is how many bits you would need to represent that number. So you can pass in an int and say, I need to know how many bits I would need to represent the number 9. And it would tell you that you need 4. So here's an example. Say you were allocating memory and you decided you wanted to do it in powers of 2. You could use bits to create these little helper functions that tell you is something in power of 2 just by counting ones. That's if the 1 bit is 1 or 0, you already know if it's even or odd, because it's the only way to make an odd number out of 2 is to add 1 to it. Or the next power of 2. So you're like 4, so the next power of 2 is 8, leave it this way. So if you're building a hash map, this would tell us, say we are expecting 1,000 items and we want to know the next power of 2, like what's the round up to whatever the nearest power of 2 is, because I want to allocate in powers of 2 for efficiency. It tells you, oh, you should make your table 1024. And that kind of logic is actually getting used by Go under the hood when it's allocating new chunks of memory when you're adding to your map or to your slice and it's running out of space and it needs to allocate another array or something like that. And the garbage collector also uses this kind of logic. This package. Okay, big. We made it all the way to big. This is the last package. There we go. Because I'm not doing random, like I said. So more math notation for fun, because I don't get to use it any other time. So we got our integers, we got rational numbers. This is something it provides us as a way to store a number as a rational number, meaning it's a ratio. It's a numerator and a denominator. It's a fraction. So any number that can be represented as an integer in the top and an integer in the bottom is a rational number. And spoiler alert, it's keeping track of 2 numbers, and one's the numerator and one's the denominator.
It's complex.
And then it gives you a bunch of functions to abstract away the fact that you're thinking about both of those. And then floating point, it provides a way to track floats as well. And it has some helper types, like a word is 1 number in one of these multi-precision unsigned ints. Rounding mode, you have all sorts of options on how you want to handle rounding when you're in the big package, because this big package, I guess I skipped that. This is here, right, for allowing arbitrary precision. So it's, I want to do something in like astronomical units, but I'm computing massive distances in the universe in meters for some reason, and you need massive ints, much larger than you could store in an int64. It's going to basically be clever and give you a stack of ints that it's going to keep track of and do all the complexity to still do addition, subtraction, multiplication on those ints, even though they're massive and don't fit cleanly into a fixed set of bits.
So I'm going to assume, there's no limit, right? Or is there actually a practical limit on how big a math?
I don't know.
Yeah. I know it's, again, one of those things I've used in advent of code where it's just like, you'll get the wrong number unless you use math.big, and then it works.
Rational numbers, like having to divide and store something as a float causes all sorts of problems. But if you know you always can represent it as two integers, one in the numerator, one in the denominator, then it actually is a big int, not a primitive int for both of these. So it'll keep track of the fact that it's 1/3 instead of trying to turn it into a floating point representation of 1 divided by 3 that's like 1/3 repeated with only limited precision. So it keeps track of that, and you stop losing information. And floats allow you to do even bigger floats and even smaller floats, even closer to 0 than you could otherwise. So there's only one function that's just straight from the package, which is Jacobi. And Jacobi function is a generalization of something else. All right, go read the page. Basically, again, this is a number theory thing, and it's very useful when you're testing for primes, which is useful in cryptography. Don't be on cryptography. Also for factorization of integers, which is also for cryptography.
Do I do my own cryptography?
No.
You absolutely should.
No one believes in you, Carson. Prove them all wrong.
I think Todd's saying you should do it, then never use it, but do it for the experience of doing it.
So it gives us all sorts of functions where we can just do add, subtract. These are all mutating on the receiver, but they also return out the value that was computed. So you can say like, because now you don't have a primitive, you have like, you did new big int, and you passed in, maybe 7 to start with, because you know it's going to get really big. And so the value is 7, and you add it with another big int, and it'll mutate your value or return it. So you have all these different like quotients, modulus, absolute value. You can do all those things. Comparison, you can't just do less than or greater than now. So now we need a function that'll return out a value that's -1, 0, or 1 based on less than, greater than, or equal to. More number theory things, greatest common divisor. So you can skip that leak code problem, or I guess it's probably not in leak code. There's a Project Euler if you want to do math problems specifically in code. I'm sure it's got that on there. And then probably prime, which is what I was talking about. So under the hood, probably prime is running different methods of prime detection. They are not 100%, but it's a strong indication that this number is prime or not, and I can't remember. The different methods are either more inclined towards false positives or false negatives. And so that's going to use that Jacobi thing under the hood a lot of the time. Now we can do bitwise operations as well on these, and it'll do it for all the different integers it's tracking in its stack and give you a final result. And then you can do conversions. Sometimes you'll lose information this way though, to bytes or strings or whatever for serialization or marshalling, unmarshalling, etc. Same thing for float. We have fewer operations, but add, subtract, multiply, quotient, because we're not going to call it divide, because whichever one of the three people wrote it first decided that was the way it should be.
We won't use the vowels in complex, and we're not going to call it divide.
You have a lot of control over the way rounding and precision happens, because there's still going to be rounding and precision with these big floats. You can control that if that were important to you. Again, conversion stuff. And then rational, which I think is the more interesting one, because it's now trying to keep information for you of numerator and denominator, and allowing you to do things like add, subtract without tracking those separately. It's all together. You know you're not going to have a bug in your code because you forgot about the denominator. You can get the numerator, the denominator out. You can set it. You can change values. You can get values out. It can tell you if it's an integer, if there's an exact integer that could represent it before you decide to cast it to an integer. Which you will see an example of casting to an integer here. So here, back to my example of 1/11. So before we did 1 divided by 11, we had a float. We added it to itself, so we had 10 operations. We had 11 of these, and we got 1.000002 or 4 or something like that. So now we're going to have a rational number, and it's going to know it's got a 1 and an 11. it's gonna keep track of the fact that it's a fraction instead of trying to turn that into a float. And then we're gonna add it to itself. This time I did a for loop.
Nice.
Sorry myself there.
Such growth.
I don't know if anyone's put this syntax into an LLM, but every time they're like, you can't do that, that's not gonna compile. They should get with the times. Yeah, we've come a long way since the beginning of the talk, and now I'm doing a for loop. And ideally this is 1, so it should tell us it's like 1 over 1, because it's still irrational here. Is int should be true, and then if we, oh, I already ran it, this is embarrassing.
Yeah.
You're all like, the big reveal is
Spoiler.
spoiler, and then the value is 1, you can cast it to it. I created a new big int. I used the quotient to say this int is this number over this number, which if it weren't something to be represented as an int, it would be cutting to an int, an actual integer, and then it's 1. So now we don't have rounding error.
Yeah, so rational.
Another example for big. So Fibonacci numbers is, again, classic example that you're probably not using. Maybe for your sprint points, you're estimating your tickets in Fibonacci numbers, and you want to know what's the first valid sprint point number in your system that's 100 digits long because it's decades of work.
Screw with your PO.
So here we're going to use that comparison because we can't just do an outright less than or greater than, but we're going to just set 10 to the 99. And once we've surpassed it, we know we have a 100-digit number in base 10. So if we're adding, do the Fibonacci computation, the last 2 numbers, add them, we're swapping them so that the order I did it in. Anyway. So then when we're done in our loop, we should have a 100-digit Fibonacci number, which is going to be way bigger than we could represent in our 64. And then we're going to go ahead and do that prime test. This is going to use the Miller-Raven test, and we're going to use 20 rounds because it's a numerical method, so you define how many you want to do. And the more you do, the longer it takes, but the more certain you are that it's prime or not prime. And it's not. It's probably not. It actually isn't. This is the first number in the Fibonacci sequence, 100 digits long. So that was cool that we could do that. Now you know. So then, and if you have a team that's sadly spending lots of your time deciding how long the work will take instead of doing the work, you can just troll them and say, this is the size of the ticket. You can tell how I feel about sizing tickets and backlogs.
This is as accurate way as any other way.
Yeah, but this way is more likely to get you fired.
Well, if you show them this, show somebody that doesn't know what they're doing, this code, and say, this is how I computed how much time it's gonna take me, they'll assume that, like, it's like, look at all that computation happening to figure out your time estimate, like, it must be an accurate estimate.
Yeah, you put in a lot of work. You
Yeah, look at that.
documentation to show you.
Complexity is correctness. We all know that.
That's exactly right.
So,
I like that.
thank you for bearing with me for, let's see, yeah, we got all the way to an hour here. Let's log through the math packages. We went through a lot of questions. I'm happy to answer questions up here if people have them. If you think you have a question that's interesting enough that everyone wants to hear it instead of starting to talk to each other, you're welcome to raise your hand. That felt like a trap.
Wow. So much judgment and nobody's even asked a question.
Who do you think you are? That's my
Let
question.
me start over. Any questions we haven't covered at this point? Hopefully you learned something about math. Yes,
I was
question.
gonna ask you, this is more like a personal question, but where did you like learn this math? Like, what kind of schooling did you go through to learn all this?
Yeah, I have a degree, a bachelor's degree in applied and computational mathematics. And so, I mean, some of this is stuff I never even really had to deal with. Especially I didn't go deep into number theory or abstract algebra or cryptography because I don't want to do my own cryptography. I And there's a lot of it in there that serves that purpose and that functionality. And like big ints, again, like generating a really big random prime number, that's important part of our security. So quantum computing's real.
That also, yeah,
Yeah.
sorry, one more question. Yeah, that actually reminded me too, like, you mentioned, you brought up like photography a couple times during your presentation, and I do photography more like as a hobby. What kind of connection have you made with mathematics and photography?
That might have been just a misunderstanding. I was saying cryptography.
Oh, cryptography,
But, we can talk if you want about photography and mathematics. Lenses, optics, you can do some of this to distort your photography, do different operations. You could,
Yeah, you can totally do your own photography for sure. Like Todd, I agree with what Todd was saying. Let's do your own.
I can show you some of the,
Similar
I mean, I'm happy to show you some of the pictures I've taken.
Instead says no photography, but do your photography.
Any other questions?